take a look at continuous distributions. Specifically, we'll have a look at the exponential and gamma, which are somehow linked, the normal and log normal, which are linked again, and the Weibull. So the first on the list is the exponential distribution, which has the following common usage. If you're measuring time, so a random time, but when the probability that the event whose occurrence you're measuring, if the probability that it happens does not depend on the past, so it doesn't depend on the time already elapsed, then this time, which is random, is well modeled by an exponential distribution. So what we mean by that is that perhaps you're at a certain time here, and you're waiting for a certain event to happen, and it's going to happen in the future, and you don't know when it's going to happen. But now, if as time goes by, so the event still hasn't happened, and you're measuring the time. If as time goes by, the fact a lot of time has elapsed already, so let's say you're here, doesn't change the prospect of the event happening earlier. In that case, the time till the event could be well modeled by an exponential distribution. And this is the so-called memoryless property. And we can write it mathematically. Well, there's many ways to write this property, but one convenient way would be this. The expectation of x, okay, where if, for instance, x is the notation you use for exponential random variable, and we'll see that it has only one parameter called beta. But so if x follows the x here, if it follows the exponential distribution, then the expectation of x conditional on what? On the fact that x is at least bigger than something, at least bigger than a certain time. Then this will be equal to simply this time, which you have, which you know has already elapsed, because you know you're on the conditional expectation that x is already bigger than t, plus what? Just the expectation of x originally. Okay, so again, on a timeline, this would mean that, well, at time 0, you start to measure your expectation for how long it's going to take to observe the phenomena. Okay, at time 0, e of x. Well, the expectation for the time is going to take is just e of x. But now, if some time passes and then you're at time t and the event still hasn't happened, well, at this time, the expectation of the time the event is going to take to realize is going to be t, the time elapsed, plus once again expectation of x. Said otherwise, the fact sometimes some time has elapsed doesn't mean that the phenomena is going to be observed soon or sooner. We're gonna revisit this concept once we see the concept of hazard rate. We're going to see that this is equivalent to saying that this random variable has a constant hazard rate. But let's see that some other time. Of course, here there's a note that for humans, that's totally unrealistic, right? Because this memoryless property essentially means that there's no aging, right? As the time passes, the likelihood that the event happens is not increasing, meaning that, well, for a human, if for instance you're measuring the lifetime of a human, so x, your random variable, is the total lifespan of a specific human or any living creature, I suppose you could say. Well, the exponential is not realistic because, of course, humans age. What I mean by that is, consider a human aged, I don't know, 10. Okay, so a kid. What's the probability they die in the next 10 years. But for someone age 10, it's not that high because, well, at least in a developed country, the kids don't often die, okay, which is a good thing. So then if someone is 10, the probability to die in the next 10 years is not very high. But consider someone who's very old already. So consider someone who's old, who's aged, let's say, 95. Okay, and what's the probability someone aged 95 is going to die in the next 10 years? Well, of course, it's going to be much, much higher than for someone aged 10, because we know that not that many humans survive after, let's say, 100 or 105 years. All right, so for a human life, there is aging, so the exponential is not realistic. Now, so this is just for some context, but in terms of mathematics, well, remember that for continuous distributions, we use this little f of x, which is the density function. And so in the case of the exponential, which, as we said, has only one parameter, so it's kind of, in a sense, a simple distribution because it only has one parameter. The density is given by this expression. If you plot what this density looks like, and by the way, it's defined for non-negative x. If you plot it, it has a sort of, well, it's decreasing and it's constantly decreasing. So obviously it's asymmetric. We have for the exponential, we have an elegant formula for the CDF. So remember, big F is the cumulative distribution function, meaning that the probability the random variable smaller or equal to little x, given by this expression. Well, this expression here. Well, it's 0 if little x is smaller than 0, of course, because the range of or the support of possible values for x starts at 0. But otherwise, if little x is not negative, then you have this expression for the CDF. And the expectation is 1 over beta. So remember that beta is this parameter. The expectation is 1 over beta, and the variance is 1 over beta squared. Again, we don't prove these things, but if you want to try, it's not especially hard. I think you just need some sort of integration by parts. You can find expectation of x with the usual formula. You integrate over the full domain or support of the random variable. You integrate what? Well, little x times the density. Well, I said I wouldn't do it, and I will not do it. I refuse to do it, but you can see that you get the integral that's, well, not the easiest, but it's not too nasty. You see that you have an x here and an exponential here, so you can solve this by integration by parts. Now here is again a numerical example. Assume that the time to failure of a calculator is exponential. Okay, with expectation 50. And they don't say the units, but then they ask calculate the probability that the calculator will still be functional in 10 years. So then you can probably guess that this means 50 years. Okay, it's very well designed, the calculator that has an expectation, well, an expectation of 50 years. So calculate the probability that the calculator will still be functional in 10 years. Well, what are we asking? Well, we're asking the probability that in 10 years, the calculator is still functional. So if x is the total lifetime of the calculator, we are here asking probability that x is bigger than 10, which is then equal to this, 1 minus the probability that it's smaller than 10, well, smaller or equal. I can write this full form, 1 minus probability it's smaller than 10. Because you know that the life expectancy of the calculator is 50 years, you know that the parameter beta of the exponential distribution is 1 over 50 by this simple relation here. And then obviously the rest is plugging the numbers. 1 minus, careful here that you have a 1 minus, and in this expression you have another 1, right? So with 1 minus brackets 1 minus this thing, and you can compute the value. And then as a sanity check, you can check that the likelihood the calculator is still alive, so to speak, after 10 years, it's quite high, like 80-something%, which kind of makes sense if you consider the fact that the expected lifetime of the calculator is 50 years. So it's kind of likely it's still alive after 10 years. By alive, I mean functional. I don't want to live in a world where calculators are alive. Although with AI these days, you never know what can happen. Just very quickly, the gamma distribution is, in a certain sense, a generalization of the exponential, because you see that it has also this parameter beta, but it has another parameter. So it's a more complex version, or it's a more complex random variable, because just roughly speaking, if you have more parameters, then you have more flexibility to fit whatever phenomena you want, because you have there's more direction in which the shape of the density function can move. And so here you see that, well, actually, you could say that the exponential is a special case of the gamma, because if you compare those two expressions, well, you realize quickly that if it happens that alpha, this other parameter, is 1, what do you get? Well, you get that you just have beta here. Here, x to the power 0 is just 1. Gamma, so I should say this notation you would have encountered before is the gamma function. So it's just a short notation for a certain mathematical function. It's called the gamma function. So don't confuse. Gamma function is a deterministic function, so it's not a random variable. So don't confuse here x, a random variable that follows what we call the gamma distribution. So this is not the same thing as the gamma function, which is just some function. But gamma of 1 is 1. And hence, you see here that you see here that a gamma with alpha equals 1 and beta equals whatever is the same thing as an exponential beta, right? Because if you plug alpha equals 1, you get exactly the same expression for the density here. The support or domain of the gamma is the positives. You have here expressions for the expectation and variance of the gamma. Obviously, they're a function of the parameters of the distribution. So you alter the parameters alpha and beta, you alter the expectation and the variance. By the way, those parameters, I don't expect you to know them. I mean, the expressions for the expectation and variance as function of the parameters, I don't expect you to know this by memory. And a further link between the gamma and the exponential is this. If you take this parameter alpha to be specifically a positive integer, so careful that it doesn't need to be. Alpha and beta, maybe I should write it here. Alpha and beta, they just need to be positive values. But if it so happens that alpha is a positive integer, then gamma alpha beta, you can see it as the sum of alpha independent and exponentials. So again, a bit like we had a link between the geometric and the binomial, the negative binomial. You have a similar kind of thing. If xi follows an exponential beta for I equals 1 up to alpha, where alpha is an integer, and if they're all independent, then the sum of xi I equals 1 to alpha, this follows a gamma. I should write a bit better. Gamma with the parameter alpha and beta. And again, so keep in mind the logic here that if every x is random, then their sum is also random. So their sum is also a random variable, which has a certain distribution. And it so happens that kind of conveniently, this distribution is simply the gamma with those parameters, alpha and beta. I say this, it's not that important. I mean, it's kind of important because you'll see it in many courses. This relation will come up. I wouldn't say it's massively important for us, but it's good that you know already. Okay, the normal distribution is a very important distribution in probability and statistics, which has those parameters, the mu for the mean and sigma for the variance. I'll just say one quick thing here, and I'll jump through this because I've made separate videos specifically for the normal distribution. Actually, I shot those videos last year, but I think they're quite or they can be helpful. So in the Moodle, you'll see them. So I'm not going to spend more time on the normal because I've already dedicated some videos to it. The only comment I need to make is that just to compare two things, the parameters here, mu and sigma, they are directly, for the normal, they are directly the mean and the standard deviation, right? So for the normal, it so happens that this parameter we call mu is directly the expectation. And this parameter we call sigma is directly the standard deviation, meaning that sigma square is the variance. But I just want you to contrast this with the gamma distribution. The gamma distribution, in that case, alpha and beta, they are not directly the mean and variance. They are defined. You can use them to find the mean and the variance, but they are not directly the mean and the variance. So this is just a comment that careful that yes, the parameters define distributions, and yes, the mean and variance are important characteristics of the distributions, but it's not necessarily that a given parameter gives you either the expectation of the variance. It depends on the specific distribution. Okay, again, I skipped this because there's a separate video on the normal. Well, here there's just a few comments that sometimes, well, if we're interested, for instance, in insurance claims, well, usually we model this with random variables that take only positive values. So in that case, the normal may not be appropriate because, well, it can take negative values, right? If you have a normal, even if the mean is something positive, so even if the mean of the normal is here, well, you know that in theory the tails extend to plus infinity and minus infinity. So this is not very well. This might not be realistic if you're modeling for instance insurance claims which take positive values. But maybe even more importantly is that usually, I'm not saying it's always the case, but it's very common that insurance claims have a very asymmetric distribution. And so, so in insurance, we often encounter distributions that are asymmetric to the right. So maybe they'll have a shape more like this. Okay? And in that case, again, the normal would not be very realistic. Okay, a word on the log normal distribution. So the log normal distribution, you could simply say the following. If, and this is actually written here, so let's start with this. If Z is the famous normal distribution, but then you create a new random variable, which is the exponent of Z. Okay, so the natural exponent e to the power of Z. Then it turns out, or actually it is the case, that's how we define the log normal distribution. And just take a second to be certain this makes sense. So if you have a random variable Z, so it's a random quantity. Now, for any specific number that's not a random quantity, you can take e to the power of this number. So you can take the power e to the power of 1, or e to the power of 2, or e to the power of whatever you like, e to the power of pi if you feel like having fun. So all of these are numbers, obviously. But so then in there, those numbers are not random. It's just 1, it's just 2, it's just pi. But in general, if you take e and you take a power that's going to be itself a random number, so a random variable, then the result is, of course, a random variable because you have e and you take a power that's random. So overall, this whole thing, e to the power of z, is itself a random variable. And in that case, and this is true in general, if you have z, a random variable, and you take any sort of function of z, then again, you get a random variable. But because f has whatever behavior, we don't know what it is, or I should say f can be anything, it's just a function. Well, f of z will have a certain distribution. And depending on which f you choose, the distribution of f of z is going to vary. And so specifically, if we have this function f of z being the exponential of z, then you're going to have a certain behavior, random behavior, and you call it the log-normal distribution. Now, I apologize because I use the notation little f, and by little f, I mean some function. Okay, I don't mean the density function. Okay, but I apologize for this notation, which is maybe a bit unfortunate. I should have chosen maybe j. Okay, so let's rewind and let's say that what I meant is that if you take any function of a random variable, you get a different random variable, meaning a random variable with a different distribution. And yeah, so that's about it. Now, but in terms of notation, you still use the same parameter mu and sigma. So you say that if z is a normal with parameters mu and sigma, mu for the mean, sigma for the standard deviation, e to the power z is a new random variable with different properties, but you still name the parameters mu and sigma. So the same mu and sigma as we had over there. And so here there's a bit of notation. If x follows a log-normal, as I said, with those parameters mu and sigma. Well, this is just an alternative notation. Then the density function is given by this big expression. Now x, so I should say this x, which is log normal, takes values in the non-negative. Yes, because of course, e to the power of whatever is going to be positive, right? E to the power of something negative is going to still give you something positive. Okay, so therefore x takes values in that are bigger than 0, and well, yeah, I should write strictly bigger than 0. And the expression of the density is this formula. Careful here to be sure you see what everything is. So x is just the argument of the function. So it's an argument of the function. So you could have called this little t. Doesn't change anything. It's the argument of the function. And then the other things are constants, right? Because you have your famous parameters. Sigma is here, sigma is here, and mu is here. Now, okay, this point, I think at first is maybe a bit tricky. What's the expectation of x? Now, the pitfall and the thing I want you to avoid, because it's a common mistake, the expectation of x is not mu. Okay, so I'm gonna, even if it's written here that the expectation of x is this expression, careful, this is a common mistake. Expectation of x is not mu. Why? Because mu is the mean of what? Of z here, and we've defined x to be exponential of z. Okay? So if we are interested in the expectation of x, we need to compute this, and there's no guarantee it's going to be mu. Okay, there's no specific reason why it should be mu. What I mean by that is, if you want to compute the expectation of x, you need to do as we always do. You integrate from 0 to infinity. 0 because you know it's a non-negative random variable. You need to integrate what this whole expression, right? Well, x times this whole expression. And you see that this whole expression contains some sigma, it contains some mu. So if you do this integral, and if if you're an integral lover, you can maybe try to do this on your spare time because it's actually quite difficult. Well, I should say, well, it's not, you can do it, right? But it's not going to take you 1 minute. It's going to take you maybe, I don't know, 10 minutes. You're going to get to an expression, and this expression is whatever is here. Okay, so it's not mu. And this kind of links back to the comment I made before. Our distributions are defined by some parameters. Okay, and sometimes it so happens that the expectation and variance, or just the moments in general, are given directly by the parameters. It was also the case with the Poisson. With the Poisson, we had this elegant thing that the expectation is just or directly the parameter lambda, and the variance is just the parameter lambda. It's not some expression of it. But in other cases, you have parameters that define the distribution, but then you compute the expectation and the variance, and you get maybe some more complex expressions for them. Right? For instance, here the expectation is this thing, then you have an even bigger, uglier expression for the variance. So the variance of x is this big thing here, which again involves the two parameters mu and sigma. And you even have the general formula here for the log normal. How generous were we to give you this expression? So for any k here, okay, an integer, you have this expression. And I should probably say, so for insurance applications, the log normal is more realistic, or in many applications, I should say, it's much more realistic than the normal because it's skewed to the right. So it's going to have a shape a little bit like this. Or I should say the shape might vary, right? Depending on the parameters, the shape will vary, but it is certainly asymmetric. So what I mean is that you change the parameters mu and sigma, and you might get quite different shape for the log normal, but in any case, it's gonna be asymmetric. Okay, and lastly, just a few comments on this Weibull distribution, which is also quite frequently used in some actuarial application, again, for maybe survival times, but also for losses and insurance claims amounts. It is another random variable that's strictly positive. Okay, so that's why, well, it's the reason why it might come up in some of our applications. And here, there's not much said about it. We just present the density function. Again, well, by now we know what the density function is, little f. Here we can remark that there's some parameters here. Again, so here there's two parameters, alpha and beta. You have this expressions for the density. Again, this is defined for x smaller than or equal to 0, because this random variable takes values that are non-negative. And you also have a convenient expression for the CDF, which is nice. In general, the Weibull is also is used for what we often call survival. So you measure the lifetime of something or someone, but it's much more flexible than the exponential, because with this parameter, with different alpha, you get very, very different shapes of the distribution, and depending on what alpha is, you can either get aging, so the lifetime. So as you age, it gets more and more likely that you die in the next couple of moments. Or you can get a constant, what we call a constant mortality, and so a constant mortality would be equivalent to the exponential distribution, because you remember we said that the exponential distribution has this memoryless property, which is equivalent to having no aging. If you measure the lifetime of something, there's no aging, meaning that as you get older, you don't get more likely or less likely to die. You have a constant, what we may call mortality. And then, but you can also have the opposite of aging, which is that as you get older, you get in better and better condition. And so as you get older, your probability to die is less and less. Now, I'm not saying this is realistic for any specific individual, but it is a behavior that you can observe in the Weibull distribution. So there's flexibility here. Okay, I think. Oh, and here there's just a comment that if you can look this for yourself, but if you plug alpha equals 1 in this formula, so imagine that alpha is 1, so there's going to be some simplification. So this is going to disappear. This you're just going to have beta. X again to the power of 0 is gonna disappear, and then you're gonna get same thing here that disappear. So you get something that's much simpler. You get 1 over beta, and e to the power of minus x over beta. So this is actually the exponential distribution, but there's just a sort of well, a relabeling of the parameter, because for the exponential we add just the parameter in front, and then e to the power of minus the parameter here. While here we have 1 over the parameter, and then here the same thing, 1 over the parameter. So this is like saying that this is in fact saying that the Weibull with parameter specifically 1 beta is equivalent to the exponential, but with parameter careful 1 over beta. But that's just a side note. Again, so this was just a side note, but in general, alpha can be anything, well, positive parameters. Okay, that's it for this video. I think I've communicated a lot of information, and some of it I don't expect you to know it from the top of your mind, or certainly not all those formulas. And also some of the properties I've communicated, they were not part of the lecture, so I suppose I don't expect you to necessarily know them, but I think it's good that I give you those properties, because they will pop up maybe in some tutorial exercises, and maybe and certainly in later courses. So hopefully that was a little helpful, and I'll stop here. And I guess I'll see you soon in a subsequent lecture. Thanks for listening.